Hey guys, this is Mr. Oliver. I'm going to be doing the solutions for AP Physics C Unit 5 review practice. So let's go ahead and get started. Okay, this first question talks about someone pushing it or standing on a circular platform that's free to rotate. The student jumps off tangentially, setting the platform spinning. What quantities are conserved? All right, so if you're on a platform, circular platform, and you're standing on the edge of this thing and you jump off tangentially, so you just leap off, you're going to apply a force to cause you to jump off that way. And as a result, there's going to be an equal and opposite reaction going the other way. So what will happen is, yeah, you're going to gain some momentum going off of this, but as a result, there's going to be equal and opposite reaction that forces this little platform to rotate the other way. And so you can almost kind of treat this as like an explosion between two masses. If you remember in the conservation momentum unit, when you had two objects sitting still initially and they separated, one would go one way, one would go the other way. In those cases, linear momentum was conserved. Well, in this case, angular momentum will be conserved. Even though you're jumping linearly, you're still part of this rotating system. And so if you cause a rotation this way, your quote unquote rotation would go the other way. And so angular momentum is conserved in this case. All right. Question number 2, you've got a bar that's falling and it goes out through this angle theta. Sketch a graph that represents the bar's angular acceleration as a function of the angle, and also sketch a graph of the bar's angular acceleration as a function of time. So what you need to think about is, as this bar is falling, the angle increases, right? And so as the angle increases, the force of gravity that pulls this down is going to be at an ever bigger angle. Okay, so as this angle increases, right, it's falling in this kind of clockwise direction. The force of gravity is acting at a bigger and bigger angle with respect to the rod. And so what happens is, the further along in time you get, this force of gravity produces more and more torque. All right. Now it's not an exponential increase. It does increase, but eventually you'll get to a kind of point where you just can't create any more torque. And so what will happen is, as it falls, you start off, well, if it's straight up and down, it's barely moving, but over time it gets faster and faster and faster. And so that means that alpha has to increase as the angle increases, right? So the further and further the angle gets bigger, the more and more acceleration you get. And you actually get some kind of an asymptote where that angular acceleration just can't get any further, right? Now, specifically, it's not really an asymptote. This is part of a sine function or a cosine function. And so if I could go past 90 degrees, let's say 90 degrees was here, it would start to go down again, right? That's the angular acceleration. Now, the angular velocity is a function of time. Well, that just kind of makes sense that the further along in time you get, the faster the speed gets. So it's kind of a increase like this. If it was a constant acceleration, this angular velocity would be linear. But because that angle increases and you're increasing the torque, the angular velocity increases also. Oops, sorry. All right, question number 3 talks about a stone falling from rest from the top of a building. Sketch a graph that represents the stone's angular momentum about point P as a function of time. All right, so what you need to remember for these kind of an objects, even though it is a single point ball and not something rotating, there is still angular momentum. Angular momentum is m times the velocity, well, that's like the linear momentum, m times v, times some kind of a radial component that's perpendicular to this motion. So if this is your radius right here, you need to figure out some kind of a component that's perpendicular to it. And it turns out that it's going to be the angle, the sine angle of this little angle right here. It's kind of hard to see. Let me draw that on a separate sheet of paper. So like if here's your point P, here's your ball of mass M, and it's falling with a velocity V, I need to trace out the angle theta right here with respect to this radial line. Right? And so if I take the sine component, this is going to be V sine theta right here. That will give me the angle that I'm looking for. And so our angular momentum is mvr sine theta, where theta is that angle with respect to the velocity. All right. So as time increases, the velocity increases, right? You're getting faster and faster. So this number right here is increasing. Does the mass increase? No. So you don't need to worry about the mass. Does the angle increase? Well, yeah, it does. As you're going down, that angle is getting bigger. So this number increases. But the sine of an angle is not that much. It's a ratio less than 1. And then R, will R increase? Well, yeah, it is. If this is it's actually going to get shorter, because as this goes down, you're going to be closing that distance right here. As this thing starts with a radius here, and you're following along this distance, if you're at this point, you're at a long distance away. If you're at this point, it's shorter, and if you're exactly opposite of point P, say like right here, you're at a shortest distance R. So this number R is actually going down. And so which one wins? Well, if you got a number that's small, but I'm multiplying by a ratio less than 1, that really doesn't change much. Whereas this velocity, the velocity that we're talking about, guys, I'm sorry, I'm off the page. If we're talking about a velocity, it follows a linear relationship with time. As time goes along, the velocity is increasing by 9.81 units every second. Whereas this thing, as the distance goes down and this angle goes up, this entire thing is just barely changing compared to this. And so what has to happen is the velocity does increase as a function of time. And it has a linear increase. Right? We're obeying this equation right here. And so what happens to the angular momentum? Well, the angular momentum has to increase corresponding to this. All right, so that's a sketch of the graph. Okay, I do have an Excel spreadsheet that kind of worked through this. I just had to double check it, and if you'd like access to that, just email me and I can send it to you so you can see. All right, question number 3. That was number 3. Number 4. We've got a ladder leaning up against a wall, and it says that the wall has no friction. Okay. The first question says, determine the magnitude of the normal force exerted by the floor on the ladder. All right, so if I draw a free body diagram of the ladder, let's draw that right here. Let's look at the forces that act on it. All right, so first of all, force of gravity acts right at the center mass of the ladder. All right, there is friction down here on the floor, because otherwise it's going to slide out, and it tells us that there's some friction. So as it wants to slide, the bottom end wants to kick out, there has to be a frictional force pointing to the left. Okay. The floor supports the ladder, so there's a normal force going up. And it says the wall is frictionless, so that means that there can't be any up and down friction from this. The only thing that can happen is that there's some kind of a wall force. It's a normal force from the wall, but there's a wall force pushing it that way. And so for the first question, it says determine the magnitude of the normal force. Well, in the vertical direction, the only forces you have are the weight and the normal force. And because this ladder isn't shifting up or down, you have to conclude that these two forces are equal. So the normal force is the same thing as the weight. All right. Now for question 5, it says develop an expression for the friction on the ladder by the floor. So the friction on the ladder is going to be the same thing as this wall force, because left and right, it's not moving left and right. So what we need to do is we need to figure out what that wall force is. Okay. So It's going to take a little bit of work, so let's just do this real quick. Let's go ahead and write an expression for um, the torques. All right, so if I look at the torques acting on this ladder right here, I'm going to choose a pivot point down here at the bottom, and I'm only going to worry about the torques that cause this ladder to want to rotate. Well, we've already said that there's a force of gravity at the center. In other words, the weight. So there's my weight. And there's also a wall force to the right. Okay. I'm going to express the angle that this ladder's leaning up right here, theta. And so that means that this weight right here actually has a perpendicular component that's going to be opposite of our angle. Right? So our weight, the weight of the ladder is going to create a torque that goes counterclockwise. So if I'm writing a torque equation right here about point P, I'm going to say that the weight times is actually going to be the cosine. I'm sorry, the cosine component of theta. It'd be the same as this side. Weight times the cosine of theta times the distance that it acts at, which is L over 2, creates this counterclockwise torque. So that's weight times cosine theta times L over 2. Okay, so that's the torque due to the force of gravity. And then the wall force produces a torque that goes clockwise. And so you'd have the wall force, Fw, times the sine of the angle, right? Because in this case, there's a component that goes like this. And so theta would be right here. It's right there in this corner. It's kind of hard to see. And so that opposite of that, this would be Fw sine theta. And so that would create a clockwise torque. So Fw sine theta times its distance, which is just L. And because this ladder isn't rotating, the sum of those torques has to equal 0. And so what we'll do is we'll take this equation and rearrange and solve for the wall force. And so you get F wall is equal to W cosine theta times L over 2, all that divided by sine theta times L. Okay, and so the L term is going to cancel, and then we're going to be left with the wall force is equal to W over 2, because there's a W over 2, times the cosine theta over sine theta. All right. And we already said that that wall force has to be equal to this frictional force that holds it down on the ground. And so our expression is W over 2 times cosine theta over sine theta. And if you don't remember, that's the same thing as cotangent of theta. And so that's your expression. All right, so let's look at question number 6. We've got a sphere at the top of a ramp. It's going to roll without slipping down the ramp. And we want to describe how the rotational and translational kinetic energy relate to the initial potential energy. Well, if you have an initial potential energy at some height h, that's UG, and then if we're rolling down a ramp, remember the kinetic energy is actually a combination of the rotational kinetic energy and the translational kinetic energy. So this sum, K rotational plus K translational, has to be equal to the gravitational potential energy. And that's true for all objects that roll without slipping. All right, question number 7. This is going to be an angular momentum equation, or a angular momentum type of problem. Let's treat this thing as an inelastic collision. So what will happen is this disk will land on this lower disk and they're going to stick together. And so if you treat it as an inelastic collision, then it's actually fairly straightforward. So we've got two objects, disk A and disk B. Disk A is the thing that's initially rotating, and the disk B does not rotate. So when we set up L initial equals L final, the initial momentum is all in A. So I'm going to say I, A, omega A, initial. That's my initial angular momentum of the system. Now afterwards, what's going to happen is when these two disks combine, their rotational inertia combines. It's like adding masses. So we'll have IA plus IB as a combination of those things. And what will happen is there's going to be a final angular speed, omega final. And that's what it asks us to calculate. So all I need to do is make some kind of relationship between these disks and figure out what the final speed would be. Now, if you remember, for a disk, I is equal to 1/2 mr squared. All right, so when I solve this equation for omega final, I'm going to get IA over IA plus IB times the initial speed, omega naught. This term up top is 1/2 times IA, so that's a mass of m, times the radius, which is 2r squared, divided by IA, which is 1/2 m times 2r squared, plus 1/2 this mass times r squared. Okay, and so when you work all this out, you end up getting the mass terms all cancel, which is nice. The 1/2 terms actually all cancel, which is also nice. And so what you end up getting is a 4r squared on top, and on the bottom you get a 5r squared, and that's all times omega naught. And once again, these r's cancel out, and so you end up getting 4/5 the original speed. That's going to be the final speed of the system. All right. Question number 8. Describe the translational rotational motion while the ball is on the ramp. Okay, so it's got some kind of translational speed. Call it a VT. And it's also got some kind of angular speed. Call that omega. Well, the only thing that can ever change these values are external forces. Well, obviously, when it goes down this ramp, there's an external force of gravity that's going to make it speed up. So VT has to increase because gravity pulls it down. However, because this is frictionless, the ball's rotation can't change because there's no external torque, no external forces that would create the torque. So omega is going to stay constant. And so it'd be kind of weird to see, but as this thing rolls, whatever that speed is, right whenever it gets to this edge, it may pick up speed going down the hill, but its rotation would still stay the same speed, rotationally speaking, as it goes down the ramp. All right, question number 9. This is kind of a continuation of the problem from the last unit, but in this case, we really don't need that much information. We want to calculate the torque exerted by the weight of the hand. So I don't care about the arm, I don't care where the center mass of the system is, I only want to care about this hand. So if I look at that in a real simple sense, here's my shoulder pivot, call that right there, and the hand's center of mass is right here in the center of that 1 kilogram block right there. All right, so if I wanted to calculate the torque, I need to know what force acts on that mass. So this is just going to be the weight, or the force of gravity of that thing. And I need to know how far away it is, r. Because remember, torque is F perpendicular times r. Now the problem is I don't want to get into all this mess of finding the angles and calculating exactly how long r is and all that stuff. So what you can do in these situations to make your life easier all you need to do is relocate this vector in a position that is perpendicular. So I'm going to treat this as my radius of r, a line directly horizontal away from the shoulder. I'm going to kind of draw this line here. This is my new r. Okay, I'm not going to use this thing. And then this weight, I'm just going to draw a line until it intersects that radial line. Okay, and so my new weight is still at a perpendicular distance away from r. I just shifted it. Because remember, vectors you can shift laterally and not change their values. And so in this case, the torque is just the weight times r, which is it's a 1 kilogram mass, so that means the weight is 1 times 9.81, and then the radius is 0.6. And so you end up getting 5.89 Newton meters of torque. Easy enough. All right, question number 10. We've got a particle of mass m moving in the xy plane at a constant speed. Okay, so this thing is moving. Let me just kind of set this up real quick. We've got an xy plane, like so. It says we've got this thing moving in a positive x direction along the line y equals 4. So 4 meters is right here. So he's moving horizontally left and right at this point. So I'm going to draw a horizontal line at 4. Okay, so this is the direction of his velocity. Okay, and it's 0.8 meters per second. That's how fast it's moving. It says, as the particle travels from x equals -3 to +3 meters along the x-axis, or along this horizontal line, calculate the magnitude of the angular momentum with respect to the origin. So that means that we could calculate the angular momentum at any point along this line, even right here when it crosses the y-axis. Now what's nice about angular momentum, especially if you've got a constant speed, the angular momentum should stay constant. I could calculate it at this location where I know that distance there, this velocity here, and this angle theta. I could calculate it along any of these lines, but really the obvious one that's the easiest is to calculate it when it's already perpendicular. Okay, so the velocity here, which stays the same at this particular angle and distance r, that's an easy enough calculation. I could do it at any point, but in this case, it's just easier to do L equals mv times the radius r. And so that's easy. 2 times 0.8 times 4. Mass of 2 kilograms, velocity 0.8 meters per second, radius of 4 meters. Right, and that's 6.4 kilogram meters squared per second. All right. If you wanted to, you could just pick any point. Like you could come over here to 3 meters, figure out what this angle is, because really the angular momentum is mvr sine theta, as long as you're taking an angle with relation to the velocity vector. All right, question number 11. We've got a spinning spherical star. It's going to lose some of its radius, but not its mass. And we want to know, pardon me, we need to know how much faster it's rotating after it loses its size. So the star is spinning and it's going to get smaller. So you can kind of think of this as like a figure skater that starts off with their arms out wide, rotating at an initial speed omega, and then afterwards the sphere gets smaller, and so the omega final will be greater than my omega initial because the rotational inertia is getting smaller. So it's a conservation angular momentum problem. And that's easy enough. You say L initial equals L final. My initial momentum, or my initial angular momentum, is I initial times the initial speed. Final. For a sphere, I is equal to 2/5 the mass times the radius squared. So here we'll have 2/5 the mass times the initial radius squared times the initial speed. Afterwards, it's still a sphere, we're assuming. It has the same mass, it doesn't lose any mass. And so we've got the final radius squared times omega final. Really nice, the 2/5 and the masses cancel. The initial radius we'll just say is r, but then afterwards, assume it's going to collapse to half of its original radius. So this initial radius we'll just call r squared times the initial radius. Afterwards, we're going to have 1/2 r squared. And so we end up getting 1/4 r squared omega final on the right hand side. On the left hand side we have r squared omega initial. And so the radius terms cancel, and the initial speed is 1/4 the final speed, or in other words, the final speed is 4 times the initial speed. So conservation of angular momentum. All right, question number 12, 13, and 14 all pertain to these two disks that are going to end up kind of collapsing it, or they're going to come together and rotate as one. So this is going to be a inelastic collision. And so in answering the first question, which properties is conserved, the only thing that can be conserved is angular momentum. If it was an elastic collision, then you could say rotational kinetic energy would be conserved. But because this is an inelastic collision, they collide and stick together, then the only thing that can be conserved is angular momentum. Question number 2 says the interval of time is elapsed from the moment of first contact between the two disks until they are both spinning at the same angular velocity. Develop an expression that gives the magnitude of the average torque that the first disk exerts on the second disk. And so in this case, when you start talking about torque and time and angular momentum, you want to use a form of the impulse momentum theorem. It's just this time it's in circular terms. And so if you remember before, it said the average force times the time interval is equal to the change in the linear momentum. So we'll do the same thing, but we'll do average torque times the time interval is equal to the change in the angular momentum. All right, so the change in angular momentum is the final angular momentum minus the initial angular momentum. That equals T average delta T. It started from rest, right? So that first, and we're talking about the first disk exerting on the second disk. Well, I'm going to only look at the second disk. Second disk. So it started with no angular momentum and ended up with some final angular momentum. So the average torque times delta T is going to be I times omega final, right? So what I need to do is figure out, well, what is this I? How do I get this final value? Well, if you think about it, that the final angular momentum is going to be the combination of the two disks because they're stuck on top of each other, right? Looks like a cake. All right, so this thing's going to be rotating around this axis. And so this final angular momentum is actually a combination of I1 plus I2 times the omega final. And so for a disk, I is 1/2 mr squared for both disks. They're both the same size. And so my I value right here is actually a combination of these two. In other words, mr squared times omega final. All right, so that equals my average torque times my change in time. So to calculate average torque, which is what we want, we just divide by delta t. So we'll have mr squared omega final divided by the change in time. And that's going to be an expression for the average torque. Okay. Now question number 15. We're at number 15. Oh, I'm sorry, number 14. Let me write this down real quick. Torque average is equal to mr squared omega final over delta t. All right. The two discs are now shifted so that the axis of rotation goes through the point on the edge of the disc. Determine the new rotational inertia. So originally we had our axis right in the center, but now we're going to change where that goes to some point on the edge. Okay. So this is going to be a parallel axis theorem. This axis is parallel to it at a distance of r away. So if you remember, parallel axis theorem says I prime is equal to I center of mass plus mh squared. Well, what was my original center of mass rotational inertia for the system? Well, from the previous problem, we saw that when they combine together, this I value is mr squared. It's 1/2 mr squared plus 1/2 mr squared equals 1 mr squared. And then over here, my mass is actually 2 times capital M, right? Right, so I got to worry about that when I do my mass right here. And then the distance h is just my radius, how far away I've moved my axis. So our I center of mass is mr squared plus my new mass, which is 2m, that's my actual total mass, m, times r squared. So we got mr squared plus 2mr squared, which is 3mr squared. That's your solution for 14. All right. Our last two questions pertain to a particle going around in a counterclockwise direction. The angular speed of the particle is given by the function shown below. So omega as a function of time is equal to bt, where b is a positive constant. So this you might kind of freak you out at first, but think about it. That is a linear relationship with velocity, which might as well be a kinematic equation. Omega is equal to omega naught plus alpha t. So this b term is really just your alpha, your angular acceleration. All right. Now, it says it moves in a counterclockwise direction, so this is going to be a positive rotation. And because it is a linear relationship, you can use kinematics. In this case, I'm not going to. I'm just going to do it with calculus, just in case I'm messing up. So if I want to find acceleration, I just take the derivative of the angular velocity. And so sure enough, the acceleration, the derivative of bt is just b. So that's important to know. Now, because that is constant, then it's like, okay, yeah, that is a constant acceleration equation. So that means that as this thing is rotating, it's not only rotating with a speed, it's actually rotating and accelerating. So this particle is getting faster and faster and faster as it goes around. That's important to know. So if it's getting faster going around, then that means that this particular point, if I looked at that particle, as it's rotating around faster and faster, it does have an angular acceleration to the left. Okay. Now, another thing that you need to recognize is that as it's going around in this circle, there has to be a centripetal acceleration as well. Centripetal acceleration is what keeps it going on that circle. And so, therefore, it does have another acceleration pointed towards the center of the circle. So, for the question, it says, draw the acceleration vector for the particle at the moment shown in the diagram. Well, it's actually a combination of these two. And so if I've got a linear acceleration to the left, that's constant, and a centripetal acceleration that's going down, which changes omega squared times r, this value is changing. My acceleration going linearly will probably be bigger than my acceleration going tangentially. All right, so I'm sorry, I meant centripetally and tangentially. So that means that my acceleration is probably not going to be at a 45-degree angle. It's probably going to be more directed towards the center. We don't necessarily know that, but it's generally the case that that centripetal acceleration is bigger than the alpha. It could be anything, but we'll just say that it's got a combined acceleration down and to the left. All right. And then the last part of the question says, what is the magnitude of the angular momentum of the particle about the center of mass? That's easy enough. L is equal to I omega. I for a single particle at some kind of a distance with mass m and radius r. I is just mr squared. Okay, so we've got mr squared, I'm using lowercase r, times omega. Well, omega was bt. So that's our expression for the angular momentum as a function of time. All right, guys, that concludes the solutions for Unit 5 practice for AP Physics C. Thanks a lot, guys. And if you have any other questions, just shoot me an email. Thanks a lot. Bye-bye.